Okay, great. So, hi everyone. I'm Shahar and I'm going to talk to you about some results that I got in tunneling measurements into 2H-TaS₂, or just TaS₂ as I'm going to call it. By the way, I'm a PhD student in Hadar Steinberg's lab, and I understand that I'm in a bit of a minority. So I'm just going to blast through the introduction because I'm going to assume that you know what a TMD is, transition metal dicalcogenide. Specifically, TMD superconductors are the materials that interest me. And you can see here the crystal structure. I'm just going to mention briefly that they have a charge density wave phase, which I'm not going to talk about, but I would be remiss if I didn't mention. They have very accessible 2D physics, and that's important because our lab is a specialist in exfoliating into very thin layers. So just as a short example, you can see here a plot that Fernando, I think, showed before. This is the tunneling experiment that was conducted into NBSE2, another TMD superconductor, and you can see the evolution of the density of states from bulk 50 layers all the way down to 2 layers. And this is pretty easy to produce because they exfoliate very easily as van der Waals materials. Also, they have very strong Ising spin orbit coupling, which I hope I'll be able to mention again near the end of my talk. Specifically, TaS₂ is interesting. It has been measured in transport before by several groups, and also in STM, but mostly it was only interesting to people because of its charge density wave, and the superconductivity wasn't an issue in most cases up until fairly recently. And the reason it is interesting to me is that it has a peculiarity. In contrast to NBSE2, which is its more popular sibling, well, what happens in NBSE2 when you thin it down is that you can see here in R versus T measurements, you can see that the critical temperature drops drastically as you thin it down. But interestingly enough, in TaS₂, the opposite occurs. So if you look here at critical temperature as a function of number of layers, this top data here is NBSE2, and you can see the sharp drop as you go down to the monolayer limit. But interestingly enough, TaS₂ has a critical temperature that increases. And funny enough, it reaches about the same critical temperature in monolayer. Now, I'm not gonna try and explain why this happens, but there's some interesting thing to notice. And it's first of all that this material has hardly been measured in tunneling. So the spectrum isn't very well known. It was measured in the monolayer limit, but not in the intermediate limit and not in the bulk. So the bulk spectrum and the intermediate spectrum are still a mystery. And well, the behavior of the gap can be interesting because as you saw before in NBSE2, you can really see a second gap developing in the transition to bulk. But this wasn't even seen before in TaS₂. So this is what I was aiming for. So first of all, I do not do STM measurements. In our lab, we do flake type devices. So we start from a substrate, we exfoliate flakes of the superconducting material on them. Here outlined, you can see a flake of a TaS₂. Then we need a tunnel barrier, so we use another TMD, namely MOS2, which is semiconducting. And now that we have these overlap regions, we can just do standard e-beam lithography and get tunneling contacts and drain contacts, and hopefully get current that looks more or less like this, and measure the tunneling density of states. This is an STEM image of such a device, and you can really see that you can get very high quality devices. You can see 4 layers of TaS₂, 3 layers of MOS2. You can see that there's very good atomic contact. These are very well behaved. So now that we have our junctions, what does the data look like? So this is dIdV as a function of bias voltage, and you can see here a very nice superconducting density of states. You can see a hard gap here where the conductivity is as 0 as we can get. And you can see the quasi-particle peaks flanking it and the drop to normal conductance. So this is a monolayer. And like I said before, the monolayer has been seen before. So we also have data for 4 layers, 11 layers, 20 layers, which is quasi-bulk. And just so you get an idea of the size of this gap, this is the spectrum of NBSE2. So we're seeing here much smaller gaps in high resolution, and this made us very happy. So now that we have a density of states, we can ask what the model that describes it is. So here we're going to look at 1 layer, 10 layer, and 20 layers. And well, you can try fitting it with a BCS density of states, which is what you would normally want to do. And you can see that you get pretty nice agreement, except for this annoying quasi-particle peak region, which is always overestimated by the model. So you could try going for a more interesting model. Like, for example, you can take an anisotropic model where delta is modulated as a function of the angle in K space, like this, and it looks a bit more like what we measured. Or you can go the extra mile and say, well, maybe this material is somewhat like NBSC2, maybe there's a second gap. So you can go for a model like a Macmillan model, which is for a two-band superconductor, and that helps it look a bit more like the measured data. But at this point, we realize that we might be adding parameters for no reason. And it seems that in DFT calculations and also in ARPAS measurements, there is no evidence for a second gap. So there's no reason to go this far. So at this point, we believe that the material is BCS or BCS-like. And what we're seeing here in this diminishing of the quasi-particle peaks is just chemistry of degradation, of being exposed to air, and not real physics of the superconducting order parameter. So right now, we believe that this material is BCS-like, but it does have this interesting behavior of getting larger and larger deltas as you thin it down. So now that we have our measurement, we have our spectra, we can ask what happens when we start turning knobs. So the first knob that we turn is temperature. So this is a spectrum of an 11-layer device as we heat it up from our base temperature of about 23 millikelvin all the way to slightly above TC, which is in this case somewhere around 1 Kelvin. And you can see that it behaves as you would expect a superconductor to behave. The gap fills up, the quasi-particle peaks go smaller, and also being pushed farther out until you get the flat line of a normal metal. And here on the right, you can see data of the zero bias conductance as it evolves in temperature for 3 devices. And we have here a monolayer, 4 layers, and the quasi-bulk 20-layer device. And over that, you can see in, okay, so the dots are measured continuously as we cool down the sample. The circles are an overlay of what we get from the individual spectra. And we have a mapping of this for something like 14 different thicknesses. So if we define TC to be the point where we get 95% of the normal conductance, we can start plotting TC as a function of thickness. So if we look at that, blue and green are my data. And you can see that we have this quasi-linear dependence that we saw before that was measured in transport, but now we have it from tunneling. And you can see that the behavior kind of saturates only at about 21 layers, which is in stark contrast to what previous transport measurements did, where they just kind of chucked everything above 8 layers as above. So the transport data that was gotten by different groups is here in red, the diamonds and the squares. And you can see that all of this mess here should probably have been spread in the middle. So we added some points here. And we can see that we more or less reproduce what was measured before. So that's nice. And now that we have TC measured, and we obviously have delta, because we have the spectrum, we can see what the relation is. So this is a plot of delta over Boltzmann constant as a function of TC. In a standard BCS superconductor, you would expect this to have a slope of 1.76. This is the black line here. Our best fit is the red line, which is 1.88. So we get a BCS-like dependence, maybe a bit higher, which might correspond to slightly stronger pairing than BCS assumes. But this is basically very similar to a BCS superconductor. The next knob I would like to show you is magnetic field. So this is magnetic field perpendicular to the plane of the sample. So I would just want to draw your attention to the fact, well, obviously blue is zero magnetic field, red is above HC2. I would just like to draw your attention to these color maps here that show you that you get normal behavior in the monolayer at about 1 Tesla. In the bulk, you get it at about 80 millitesla. So there's a huge difference between the bulk and the monolayer in perpendicular field. Also, we can look at the critical field, which we denote as a field which gives us 99% of the normal conductivity. And as a function of number of layers, you can see that you get about an order of magnitude and a half of difference. you can see that it saturates more or less in the same place as the temperature measurements. But more interestingly, you see that HC2 acts linearly in delta squared. And this is interesting because what you would expect is, well, if you take the Ginzburg-Ladder expression for HC2, you see that it's linear in 1 over the coherence length squared. And if you look at the BCS coherence length, it's supposed to be inverse in delta. So if you have a linear dependence of HC2 and delta squared, that would imply that Xi and Xi BCS, this is Ginzburg-Ladder Xi and Xi BCS are linear in each other. And that would mean that you get a clean superconductor, that's fine. But that also means that you have the same V Fermi for all thicknesses, which is interesting because you would expect the band structure to change. We can also obviously extract this V Fermi that we get here in this linear dependence. And it turns out to be, I saw that it's 11 minutes, and it turns out to be 0.36 electron volt angstrom, which is about 3 times lower than what DFT calculations expect. This is a fairly new result for us. We only just calculated that, so we didn't have a lot of time to think about why this happens, but we're reporting it. And the last thing I want to show you is some data in a parallel magnetic field in plane. So what you can see here is a monolayer that doesn't respond, well, hardly responds at all to 8.5 Tesla in plane. And on the other end of the spectrum, you have a 20-layer bulk-like spectrum that is almost normal in 1.5 Tesla. And actually, if we pushed it a bit farther, we would obviously get the critical field in less than 2 Tesla. So we have an unbelievably anisotropic response. And also, we have a very clear indication of the strong Ising spin-orbit coupling that you would expect from such a TMD. And it's pretty reminiscent of what you get in NBSC2, even though it behaves kind of the opposite in the thickness dependence. And of course, when you go thicker, you start showing more cross-section to the magnetic field, and you start getting orbital effect, depairing, and losing your superconductivity more easily. So I'd like to close this slideshow with this image that shows the stark difference in response to out of plane and in plane magnetic field, and just reiterate the conclusions. So we have something that looks pretty much like BCS, although we have the quasi-particle peak deviation. We have HC2 that roughly follows delta squared, which says that we have the same V Fermi all the way, but it doesn't agree with the number that you get from DFT. And we have very strong Ising spin-orbit coupling like we expected. And that's basically it.
Okay, Shahar, thanks. Thank you very much for the nice talk. We have a couple of minutes for questions. This time I will try not to misinterpret the hands. Okay, so maybe I can start with one question. So it's a very naive one, but you mentioned that instead of STM, you're using this flake type spectroscopy. Can you briefly comment on what are the differences and why are you doing that?
Yes, so STM gives you the local density of states. You basically tunnel from atom to atom. So what we have is these flake devices, and you basically average over an area, but you also have much finer control over the thickness of the sample that you get. You don't have to be over a conducting background. You don't need to be on graphene or gold, something like that. And you also have the ability to go colder than most STM setups that are available right now. And you get magnetic field in 2 orientations, and you can go pretty high. We have a 9 Tesla magnetic field in plane, which is better than you get in most STM setups.
Okay, that makes sense. Thanks a lot. We have a question by Dennis.
Yes, thank you for nice talk. At the beginning, guys, when you show the, let's say, suppression of the superconductivity with the number of the layers, I think you know the answer why this happens. Can you tell us a little bit more about that, or can you?
No, actually, there are a few hypotheses by different people. Some group theorize that maybe there's a second gap that opens when you thin it down. We don't see an evidence of that. There was a group that hypothesized that there may be an interplay with the charge density wave, that in some way when you go to thinner samples, the charge density wave signal seems to diminish, and then it kind of frees up density of states to go into the superconducting state. We don't know how to comment on that because we're not sensitive to the charge density wave in our setup. And another group said that they think it happens because of stronger electron-phone uncoupling, which could be true. But the answer is we don't really know. It seems like we haven't ruled out the phone uncoupling hypothesis, but we don't know how to confirm it at this point.
Okay, we have one last quick question by Luca.
Hi, yeah, so I wanted to add something about this very last question. I guess in Manchester, they showed that if you encapsulate the system, then probably you avoid the effect of air or oxidation or something like that. And then they ascribe it to some electron-phone interaction. As far as
yes, so the problem with encapsulation in this case is that you want to leave a part of your flake that's available to the drain electrode. If you don't do that, you don't have the ability to tunnel well. You need one of your contacts to be with much higher resistance. So that means that you need another one to be a good ohmic contact. And if you encapsulate and you want to still make a good drain contact, you need to etch. And if you want to do it with something thin, then you won't be able to etch accurately enough so you don't eat away your sample. So it's a bit difficult.
yeah, so I mean, do you think it's really
but this might work out if we work on a yes, I'm listening.
Yeah, no, I was just saying, do you think it's really something that is pristine of the material, so that it belongs to the material, or might be an artifact of the construction or the way it is processed?
So there's empiric evidence to show that it's probably that. If it's funny because it's not exactly physics what I'm describing now, but if when I look back on my calendar and I see when I finished fabricating a device and when I started measuring it, you can clearly see that if you don't immediately throw your sample from fab into your cryostat, you start losing height in your quasi-particle peaks.
Okay, thanks very much. I guess it's time to move on to the next talk. So thanks again, Shahar.
Thank you.